All right, so in this section, we're going to see basically a theorem which gives us what could be taken as another definition of continuity. If you've built up the sort of theory of topology, especially the topology of metric spaces like we have done so far, and you have the concepts of open sets and closed sets and so on, then there's actually a very simple way to characterize continuity, which you could take as a definition, obviously, but in our case, it's going to be a theorem that the property that I state about open sets and continuous functions is going to be equivalent to continuity. In my opinion, it's one of the more important ideas that we cover in the entire class, especially for anyone who's going to continue studying math at all in any level of abstraction beyond what we deal with in this class. This idea about continuity and open sets is going to be very foundational for topology, for analysis, for all sorts of other areas in math. So yeah, and I think it's very beautiful. Also, I will say that since we're going to be talking a lot about inverse images, it'll be good for you to be familiar with that idea. And if there should be a video, which is sort of another note about functions that talks about inverse images and stuff. If it isn't posted by the time I post this lecture, it should be available very shortly after that. I suggest maybe you watch that first before you watch this. But yeah, anyway, so let me state the theorem here. So let S and D, S star, D star be metric spaces, and F from S to S star a map between them. Then F is continuous if and only if so F inverse of U, or the inverse image of U is open in S for each open subset U in S star. Okay, so basically just whenever you take the inverse image, remember inverse image, okay, not the inverse function, which may not exist, okay? F may not have an inverse function, but you can still take the inverse image of any set in S star, and you get a subset of S. And so it turns out that it's enough for F to be continuous. It's equivalent to any open subset of S star mapping via the inverse image to another open subset in S, okay? So I'm gonna go to a new page and I'm gonna draw a picture real quick to kind of sketch this idea. Okay, so I drew a little sketch here of, a situation where if we just kind of, we can literally imagine that, S star and S might both be just copies of the real line. And so I'm kind of showing you what our inverse image concept here, right? This inverse image property looks like for familiar functions, okay? Because it's easier to visualize what it looks like. But of course, since S and S star could just be arbitrary metric spaces, the picture might not really look like this at all, but it's just supposed to be instructional. So what you see here is I picked a random open subset in S star, right? And then I found the inverse image of that. So here's the graph of the function, right? And I found the inverse image of that open subset. And it turns out that it's also an open subset of S, right? And the reason specifically is because since this is open, these endpoints in S star, right? U is just like two intervals in S star. And since the endpoints are open, that means that like, you know, the way you find the inverse image is you go and you look at like, what are all the points of the graph that are like in this, you know, band here, I guess, right? That's, those represent places where the values of F fall within U, right? So here's a, for example, here's a place where the values of F fall within U, right? And now because U is open on this end, right, or this endpoint here of this interval is open, these, I drew circles here to represent the fact that like those points are not actually included in U, right? I mean, those points in the graph don't fall inside of, or those values of the function do not fall inside of U because these endpoints are excluded. So if you think about it that way, what you have here, the piece that's actually inside this band is kind of like a little curved segment, but it's open on both sides, right? So then when you project it down, when you look at the X values that correspond to that piece of the graph, the endpoints are also missing in that case, right? And the same thing is true for all of them, that you end up with these open endpoints in the domain. And so the result overall is an open subset of the domain, which is just a union of a bunch of these intervals, right? So starting with this U, which was open, it was a union of two open intervals. We ended up with another open subset of S by finding the inverse image, okay? So the idea is that you could pick any open subset over here, and then the result of this process would be another open subset down here, okay? So yeah, it's not, it probably shouldn't be immediately obvious why this ends up being equivalent to continuity, but that's going to be the point of the next, or of the theorem that we prove. Okay, so let's go ahead and prove this theorem. And actually, well, okay, yeah. So let's just start on the proof here. Okay, so let's start the proof. I drew another picture to kind of help explain the argument a bit, so you can kind of visualize it. Of course, again, remember, this is not actually what it looks like because S and S star are arbitrary metric spaces, but it turns out that to build the argument, it's actually enough to just examine this picture. You'll come up with all the logic necessary, and that logic will apply to an arbitrary situation. So we have to go two directions. Let's start by assuming, suppose F is continuous. Okay. Now, we want to show that the inverse image of any open set is open. So let U be an open subset of S star. So we want to show F inverse of U is open. The inverse image of U is open. To show, right, remember, remind yourself right now, actually, what the definition of being open is, right? A set is open when every point in the set is interior, right? So if we want to show that F inverse of U is open, we should just show that every point in F inverse of U is interior, right? So let S naught be in F inverse of U. To show that it's interior, right, what does it mean to be interior? It means that you can find a radius around S naught so that the ball of that radius is contained entirely inside F inverse of U. So want to show that there exists an R, or let's call it delta, such that the ball of radius delta around S naught, the open ball, right, is a subset of F inverse of U. Oops. Right. So how do we do that? Okay, well, we have to use continuity, right? I mean, that's the point. So first of all, right, so in the picture, right, S naught is just some random point in F inverse of U, right? So the point is like this question mark represents, this is ultimately what we're trying to find, this interval around S naught of radius delta, right? And so basically the idea is, well, F of S naught, by definition, it has to be somewhere in U, right? And that means that it's interior to U because U is open, right? So we know U is open. So all the points of U are interior. So that means that there is some kind of an open, there is some kind of a ball around f of S naught. And then the point is that if you think of the ball as being radius epsilon, then the question of whether there's, whether there's a delta so that, this bubble here is contained in the, bubble. Well, actually, okay. My actual radii might not match up with each other, so let's be careful about this. But the question, so let's see. So yeah, it's almost perfect. So let me just quickly adjust these. So the delta has to be a little bit smaller from the picture, at least, than I originally had it. Okay, anyway. So, but right, the idea is that if we can just find a radius so that the image of so that all the values on that smaller radius fall within this, radius epsilon ball around f of S naught, then of course they all fall within U. So that means that this this neighborhood, this ball, would be a subset of f inverse of U, right? So note that f of S naught is interior to U since U is open. So there exists an epsilon greater than 0 such that the ball of radius epsilon around f of S naught is a subset of U, right? Then, since f is continuous at S naught, there exists a delta such that f of the ball of radius delta around S naught is a subset of the ball of radius epsilon around f of S naught. Okay, now I know I didn't really phrase the definition of continuity this way before, but if you think about it, this is exactly what the definition of continuity is saying, is that given any epsilon, right, there exists a delta such that for all points within distance delta from S naught, right, and the set of points within distance delta from S naught is exactly the ball of radius delta, right? So the delta exists such that the set of points within distance delta from S naught, if you evaluate the values of f on those points, are no further than epsilon away from f of S naught, right? So that this is exactly the, so this is just a rephrasing of the epsilon delta property. Okay, so you should definitely, maybe you can think about the picture shows exactly how that's true. So like this delta we found just so that like the values, right, the values of the function on this ball of radius delta here all fall within this ball of radius epsilon around f of S naught, right? That's the idea. That's what the epsilon delta property guarantees us. So then delta is the desired radius, right? To show that S naught was interior to f inverse of U in the beginning, right? Delta is actually the radius that we need, because if the ball of radius delta around S naught is, if the values on the ball of radius delta around S naught are a subset of this ball, then that means that all of the values on, right, because this ball is a subset of U, right? So all the values on f of b delta of S around S naught, all of those values are in U. That means that all of the points in b delta around S naught are in f inverse of U, okay? So B delta around S naught is a subset of F inverse of U. That's exactly what we want, right? Okay, so that's one direction. I'm gonna erase this argument, and I'm gonna modify the picture a little bit. Okay, so now let's just suppose that we know that the inverse image of any open subset of S star is also open, okay? So then the question, so we want to show that F is continuous at every S naught, right? So that just boils down to showing the epsilon delta property, right? So let's let epsilon be greater than 0. Now the key insight here is just to notice that the ball of radius epsilon around F of S naught is an open subset of S star, right? So then B epsilon of F S naught is open. So the inverse image of B epsilon. So this is, in fact, yeah, let me just label this here. This is B epsilon of F of S naught. And then down here, what I've drawn is the inverse image of B epsilon F of S naught, right? So this is the inverse image of B epsilon of F of S naught. And we know that, so since B epsilon F of S naught is open, then the inverse image is also open, right? So F inverse of B epsilon of F of S naught is also open. So that means that S naught is interior, right? S naught is interior to F inverse of B epsilon of F of S naught, right? And so what it means to be interior, okay, there exists a delta such that B delta S naught is a subset of F inverse of B epsilon of F of S naught, right? But if B delta is a subset, if B delta of S naught is a subset of this inverse image, that means that the values, so F of B delta of S naught, are a subset of B epsilon of F of S naught, which is what we wanted, right? Because remember, so like if this is a subset of the inverse image of some set, that means all the values of F on this set have to be within the set inside here, right? That's just by definition of, that's just how inverse images work, okay? And just remember that this here, this statement, F of B delta of S naught is a subset of B epsilon of F of S naught, is exactly just, you know, an encapsulation of the epsilon delta. That's the predicate, the conclusion in the epsilon delta property, right? Is that for every point within radius delta of S naught, right? That's a point of B delta. The value of F at that point is within radius epsilon of F of S naught, right? So that's exactly what we wanted to find to verify the epsilon delta property. And that means that, or rather, sorry, that shows that F is continuous at S naught, yeah. So yeah, that's the theorem. Okay, so the very last thing I want to do in this video is give you a little question. So this would be lecture 15, question 1. So we've seen that the function f of x equals sine of 1 over x for x not equal to 0, and 0 for x equals 0 is not continuous. Note that this is defined everywhere on R. So the domain R. Okay, so we've seen that this is not continuous at x equals 0. Find an open subset of R, open subset, let's say U, such that F inverse of U is not open. Okay, so pause the video, think about it for about 10 minutes maybe, and write your thoughts down, include it with your homework, and when you unpause, I will solve it. Okay, so one answer for this, I think the answer that's sort of easiest to verify, at least visually, would be just the set u equals -1, 1 is a good one, because, or rather, actually, even better, even easier might be -infinity to 1, because that way you don't have to deal with extra missing points. So let's say u is -infinity to 1, right? This open interval. Then f inverse of u is basically R without the points wherever f equals 1, right? So where is f equal to 1? That's when x is like pi over 2 plus 2 pi n. So, or sorry, when x is 1 over pi over 2 plus 2 pi n. So R without the points 1 over pi over 2 plus 2 pi n for n n equals like I guess n in z, right? So right, so you can see that there are, so if you think, so then 0 in this set, 0 is in this set, right? Because f of 0 is 0, which is in U, obviously, right? But 0 is not interior to U. If you draw a picture, okay, it looks like this. So, right, the wave, well, I'm not gonna draw the wave. Well, okay, I'll try to draw the wave. Right, so, and then it gets like really close to, or it gets really, it oscillates really fast, right? Something like that. Okay, so here's 1. So f is supposed to hit 1 at these points, right? So if you draw f inverse of u, so here's f inverse of u, you're just missing a point wherever f happens to hit the value 1, right? So if here's 0, then, there's a, well, I guess I should align it. So if this is 0, then like here's a point missing, right? Here's a point missing. Here's a point missing, right? And so on. And then there's like an infinite number of points missing close to 0. And similarly, out, as you go further and further out, every point where f is 1 is just missing from the inverse image here. So 0 cannot be interior because, right, no matter how small of a radius you put around 0, there are going to be some missing points from f inverse of u in that radius, right? So that's why the set is not open. And of course, any open set, like for example, any set like negative epsilon to epsilon with epsilon less than or equal to 1 also works. So you could do like -1/2 to 1/2, -1/10 to 1/10. All of those would work because basically what would happen is instead of these little points missing, you just have like open intervals missing from the, or rather closed intervals missing from the domain here. So it won't be open. So anyway, that's it for this video. In the next one, we'll do some generalizations of the basic theorems that we have about continuous functions for metric spaces.